Alrighty, I'm going to talk a little bit about some rules of exponents. And the first thing before I even go into the rules, I do want to talk a little bit about some of our basics about exponents. So first of all, let's talk some terminology. The number that we multiply, so an exponent is just a way of writing repeated multiplication. The number that we're going to multiply over and over is called the base. The number of times that we multiply it, that is our exponent. And if I were to expand this out, this would be 5 times 5 times 5. This is sometimes referred to as an expanded notation. And then, of course, our answer is, once again, a product. So 5 times 5 is 25. 25 times 5 is 125. And so the answer, what we think of as an answer is, of course, the product. Now, one thing I do like to point out is there is no such thing as a naked exponent, so you can't just have an exponent. Notice that this 3, I'm never multiplying any 3's in here. I am multiplying 3 times, but I'm not multiplying the number 3 at all. The other thing I want to point out, and this is going to be fairly important, is that exponents only apply to what they touch. Now, this seems like it's a no-brainer. This might seem like a statement like, okay, sure. But the funny thing here is the exponent is only going to be attached to a variable or a number, and it won't necessarily include the sign. So with this, kind of what this means is watch your parentheses. Because if I've got something like, say I've got -3 squared, this is not going to be the same as inside a set of parentheses, a -3, and then a square there. Here, this is literally just, this exponent is only applying to the 3, and it doesn't apply to this negative sign in front of it. In some ways, you could almost think of this as like -1 times a 3 squared, and this would be -1 times, 3 times 3. That would end up being a -9. Now, that is not going to be the same thing as just, well, this is just a -3 squared. Oh, that's going to be -3 times a -3. And of course, a negative times a negative is a positive. So when you're doing that, note that the parentheses are extremely important. That's a very useful distinction to make. Okay, enough with our basics, and let's move on to some of our rules of exponents. And the first one we always are going to want to go over is what we call the product rule. And the product rule is just what happens when you multiply two terms with the same base. So this is essentially what happens when you multiply two terms with the same base. You're going to add your exponents. Or the succinct way of writing this is that, x to the a times x to the b is equal to x to the a plus b. And I think that if you start thinking about what this means, what this looks like, is that I'm just combining my multiplication. So it's a little bit like saying, oh, x to the 4 times x to the 5 is going to be x to the 9. And the thought process that kind of goes behind this, so I'll draw our little thought bubble here, that x to the 4 times x to the 5, that's going to be x times x times x times x. There's 4 of those. I've got x times x times x times x times x. There's 5 of those. And then we just count up how many x's am I multiplying altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's x to the 9. This is the reasoning behind this. So this is our product rule. And we can do a lot with that. But now let's move on to our next basic rule. And this is, of course, our quotient rule. With the quotient rule, this is where we're dividing to, if we are dividing, excuse me, two terms with the same base, we're going to end up subtracting the exponents. Now, there's a couple things that are going to go with this. So I usually do at least 2 different versions of this rule. So first of all, let's do the succinct version. Let's do one of these. So let's say I've got x to the a over x to the b. This is going to be x to the a minus b. Now this is true. This is the first version of this rule. This case, for this, I'm going to note that this is really helpful when a is bigger than b. This is, so you've got your larger exponent in the numerator. So an example of this would be if I had, say I had x to the 6th over x squared. This is going to be x to the 4th power, or 6 minus 2. And once again, our reasoning behind that is, well, this is a fraction. And just like any other fraction, things will reduce. So that x to the 6th, that would be x times x times x times x times x, 1, 2, 3, 4, 5, 6. And then I'm dividing that by x times x. And when I reduce, of course, I am basically saying, well, a thing divided by itself is 1. Okay, I've got 2 separate 1s there. So I've got 1 times x times x times x times x times x all over 1. So this is, x to the 4th over 1, or just x to the 4th. Oops, running myself out of space. So that's the reasoning behind this. Well, what happens, and this is the other piece of this rule, is what happens when we've got a higher exponent in the denominator. And there's 2 different ways we could go about this. I am going to show you my preferred way. And my preferred method of doing this is if we've got, x to the a over x to the b, this could also be 1 over x to the b minus a. And this is going to be true when that, whoops, I somehow made that into a subscript rather than an exponent. So this is going to apply more when b is the larger number. So when we've got this is when we've got the larger exponent in the denominator. So with this, I can show you the example where, let's say we've got, say I've got y to the 3rd over y to the 5th. This is going to be 1 over y squared, y to the second power. The reason and if you're ever having trouble figuring out which one you use, just say, okay, I know I'm going to be subtracting these. Where is my larger power? That's where the term ends up. With our other, here, I've got my larger power in my numerator. And in some ways, I could think of this as still in the numerator. So I've got my results. I've got my term with the higher power right there in the numerator. Here, I've got my results, and my remaining power is in the denominator. My higher power is in the denominator. And once again, our reasoning stays the same. And we'd expect that it should. Y cubed would be, y times y times y. Y to the fifth would be y times y times y times y times y. And just as before, our like terms cancel. So when we cancel, y divided by y is 1. So these essentially become 1s. 1 times 1 times 1 is 1. 1 times 1 times 1 times y is that y to the second power. So this is the reasoning here. Now, from this, if folks have figured out, wait a minute, can I still just do this subtraction as I normally would with, could I still do this a minus b? We sure could. And this brings us to one of our first things, and this is with a negative exponent. If I've got, x to the a over x to the b, we could still do this x to the a minus b anytime. But if a is smaller, then this is going to be a negative exponent. So for example, say I've got h to this h squared over h to the 7th. This could be now 2 minus 7, that could be h to the negative 5th power. Now if I apply this rule, we'd also see this is going to be the same thing as 1 over h to the 5th. A negative exponent has some specific kind of ramifications. Anytime I've got a negative exponent, the main thing that a negative exponent does is it takes the reciprocal of that term, of that one variable. So let's let me go over. Actually, yeah, let's explore that just a little bit. So with negative exponents, ENT, negative exponents. Negative exponents have a couple properties, and the main thing is it's going to be a reciprocal. So if I've got, say I've got x to the negative a, this is going to be the same thing as 1 over x to a positive a. So all we're doing is we're taking the reciprocal, we're flipping a fraction, and then we change the sign of the exponent. If I've got 1 over x to a negative b, this is going to, once again, we're going to flip this. So we're flipping our term, and we're changing the sign of the exponent. So this is a really, really helpful tool for us. Now, the other thing is, well, if we're thinking of reciprocals, so this is one of our first rules. These are our first two rules. We've got also what happens if I've got like x over y. I'll see if we can separate these out a little bit. X over y to say negative c. Again, like I say, we're taking a reciprocal, so this is going to be the same thing as y over x to a positive c. The main thing with a negative exponent is it takes a reciprocal. Last, I've got one more sort of major rule, but I do want to bring up another. Actually, I guess I'm going to go over two rules. One other thing from our quotient rule is we have something called the zero power rule. And this one can sometimes confuse people. The zero power rule says that any non-zero base to the 0th power is 1. So that means that x to the 0 power is equal to 1. And that might seem very weird. It can seem very unusual if you're not but that's probably because you're thinking more of this as multiplying by 0. You're not multiplying by 0 again. You're multiplying 0 times. So technically, one of the ways that we could think about this, but let's go through some examples here. And the nice thing is, this is one of the easiest ones to apply. So if I've got, say I've got, z to the 0th power, that's 1. I've got 5 to the 0th power, that's 1. I've got negative 22 and a half to the 0th power, that's 1. Where it gets interesting is where we've got when we add a coefficient in here, because remember, the power only applies to what it's touching. So if I've got 3, let's say I've got like 3x to the 0, that's just going to be 3 times 1, which is just 3. If I've got negative 2 times x plus y to the 0, that's just going to be negative 2 times 1, or just negative 2. So this is the source of many dirty tricks that math teachers love to play. Now, I imagine some folks wondering where this comes from. So let's show you some reasoning behind this, or a way of thinking about that. And let's start by saying, let's do like 3 to the 4th power over 3 to the 4th power. Now remember, if we are using just our quotient rule, I can take these two powers and I can subtract them. So this is going to be 3 to the 0. But I also want you to think about what that's going to look like. 3 to the 4th, that's 3 to the 4th over 3 to the 4th, 3 times 3 times 3 times 3. That's going to be 81 over 81. And anytime you've got something divided by itself, the answer is 1. So essentially, when you say you're taking something to the 0th power, you're essentially asking what happens when I divide this number by itself. So that's what's happening with our 0 power rule. Okay, last basic rule, and then I will let you guys go back to your lives. And that is this. We have the power rule. And the power rule is this. This is where we're dealing with an exponent to an exponent. A term with an exponent inside parentheses to a power that's set to a power, and that's going to be outside the parentheses. What you're going to do is you're going to multiply the exponents. So the short way of saying this, x to the a. So this is inside the parentheses. Now I've got a power outside the parentheses. Notice that I'm only writing my base one time. This is going to be x to the a times b. So what this means is if I've got, say I've got x cubed to the 5th power. This is going to be x to the 15th. So once again, I'll give a reasoning behind this. I'll give you an example, that sort of concrete example. This is x cubed to the 5th, so x cubed to the 5th. So this is going to be x cubed times x cubed times x cubed times x cubed times x cubed. And if I really want to be incredibly pedantic, I could say, okay, x times x times x, there's that first one, times x times x times x, and so on. X, and then keep going, x times x times x. I'm running myself out of space. So yeah, that's where we get to, then just count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I've got x to the 15th power. So this is how the power rule works. Alrighty, that's all I've got for you guys right now, and I will see you in the next video.